quiz where we had to identify what was wrong with the picture. And this is that same sort of diagram. It does a good job of showing us, something about orbits. We see them all orbiting the sun, but the scales are all wrong. Planets are not crowded together like this. Okay, so we're going to start our discussion about orbits, talking about a historical figure named Johannes Kepler. All right, so we left off talking a little bit when we talked about the solar system models about the history of astronomy, which you probably took note really became modern astronomy at the end of the 1400s, so the end of the 15th century. All right, so remember we had a ancient model that dated back to the Roman Empire at that point, but also the legacy of Greek science. But most importantly, it's the ancient world, right? So we a real kind of demarcation in terms of human advancement. And then after the so-called Middle Ages, what scientists often talk about as a era of stagnation, which was probably due to a series of really bad luck that humans encountered throughout those hundreds of years in terms of a plague, extreme weather conditions, something that they call the mini ice age, and that just set kind of made it so people couldn't, kind of reestablish the level of civilization that the Romans had had, which I always find to be such a fascinating idea that you could have all of the Earth and no one is as advanced as this dead civilization that you see evidence of. It's so different than the world that we live in. But then the so-called, modern era kind of starts off, the Renaissance, if you know that term, is associated with the 15th century, which would be the 1400s. And we'd already talked about Galileo because of how his science and his findings came right after Nicholas Copernicus in terms of their lifespans and proved the heliocentric model. So Galileo is famous for proving the heliocentric model. Okay, but now we're going to introduce some new characters in our drama of astronomy. We have a gentleman and quite literally a nobleman, I'm sure you would have been called at that time, uh, named Tycho Brahe. He was Dutch. He lived in a mansion, and he spent a lot of his great inherited wealth on astronomical, his astronomical passion slash hobby slash obsession. Um, So he was think of him as a rich eccentric living a life of leisure, didn't have to work, and he just poured all of his energy into making observations of the night sky. In in many cases, that wouldn't go anywhere, and we wouldn't talk about such a character, right? We don't typically talk about someone like that. But all of those observations that he made ended up being just crucial to the establishment of what we now know about orbits. And he wasn't the one that made the breakthroughs, but he was the person who made all the observations, made many of them himself, and really and also just like it made saved them, put the money in, and so on. Also had a menagerie of animals living in that mansion with him. So, real walked around in robes, just to think really, really strange, eccentric character. And he hired many assistants, whole teams of them, but one assistant that really stood out and became his right-hand man was this guy named Johannes Kepler. And Johannes Kepler, unlike Tycho Brahe, didn't come from the noble, the noble people of whatever kingdom that was in modern day Holland. And he came, from a working class family, kind of well middle class merchant, but also working class. He had to save his mother twice from being burned as a witch because obviously his family was into education, but that was not really acceptable for women to do in Holland at this time. This was kind of the Americas had their witch craze much later. This was happening in mainland Europe at the time. But luckily, he was well known enough at that time that he was able to come back from Austria, later in life and save his elderly mother. But they also might have been sort of extorting him for money. Point being was that he gets hired, as you can see, there in terms of lifespans, right? Tycho Brahe, you know, Johannes Kepler. So, he would have been a younger man when he first started working for Tycho Brahe. And then Tycho Brahe dies, right? Doesn't live a long life, you know, too much, liver, that, the gout was too bad. And then Kepler gets all of his data, right? So just like sheets and sheets of star observations, and he starts working with those. He starts using math that he created himself, and also a kind of a budding field of mathematics that was happening at this time in Europe, as well as across the Channel in England. Although this does predate the creation of calculus, despite that, they were working with the geometry that they had at the time, and he was able to establish what we know as Kepler's laws by using Tycho Brahe's observational data. He had a publication later in his life called Astronomia Nova, and that's where he laid down those three famous laws that you're about to see. So when you think about Kepler, you want to think about Kepler's three laws. And remember that he's associated with Tycho Brahe. You need to know like at least a little bit about what the names are associated with, as much as to be able to not mix them up, right? Because a multiple choice question would say what was Tycho Brahe famous for? Well, it wouldn't be creating the heliocentric model because that's Nicholas Copernicus. All right. This you can kind of see it's color coded. This was in the other timeline, and this is just what Galileo published, where he saw that Jupiter had moons, and if Jupiter has moons, then that kind of implies that not everything orbits us, right? Which is indirectly supportive of the heliocentric and rejects the geocentric model. But of course, his phases of Venus and the observations. I'm talking about Galileo now. The observations that Galileo made of the phases of Venus are more important because they're considered direct evidence of the heliocentric model. If you want to see that, those are the very last slides of chapter 2. All right, so talking about Kepler's work, this is just a mock set of observations. So imagine that these are the type of data that Tycho Brahe was observing, and it would have dates and the location of celestial bodies in the sky. In this case, the sun and Mars. And these coordinates would represent the declination and right ascension in degrees of the sun on that particular day. And likewise for Mars, we would have the declination and right ascension on a particular day. So if you took those and you plotted them on a graph where you had axes that went from negative 90 to 90 for declination and 0 to 180 for right ascension, then you could get something where you can have the coordinates, all right? And getting the coordinates in the sky, you could then translate them to what the coordinates would look like in different perspectives. Because you could say, okay, well, if I know these two coordinates, the sun and Mars, well, if I subtract one from the other, then I'm getting the angular distance, the angular displacement between the sun and Mars. And that's sort of telling me the location of Mars relative to the sun at particular points. Okay. And that's what is being shown here. The concept is being simplified because you have to deal with things like the orbital planes and adjustments like that, and some ideas that Kepler just simply didn't know at the time. But even the calculations he did would have been a little bit more involved. But here it simply would be a matter of taking that the two different coordinates and finding the difference between them. So you can get essentially this line between the red dot, which is Mars, and the yellow dot, the larger yellow dot, which is the sun. Right. So finding the difference, because both of these are relative to Earth, right? Because they're both the celestial objects as seen from Earth. So if you continue to do that, you can continue to locate Mars in an angular sense relative to the sun. And when Kepler did that, he was able to get over, the period of a Martian year, which is, almost 2 Earth years. Right? It's like, I think it's 1.8 Earth years. So, but regardless of how long it took, able to, take subsequent observations and just continue to get more dots until finally he tracked Mars over its complete orbit. So now we have a complete orbit of Mars around the sun. What shape does this look like? How would you describe this shape?
I say oval.
Yeah, exactly. Yep, oval. There's a technical term that we're going to see called ellipse, but oval is just fine. Yep, it's not a circle. All right. So the reason that that's so significant is because he expected it to be a circle. And the reason he expected it to be a circle was, although he was a big believer and advocate for the heliocentric model, that model that Copernicus had introduced, not, just a few decades ago, really, relative to Kepler's life, he still, was a religious person. He still figured that God created the universe with some amount of perfection. And the fact that the orbits wouldn't be perfect circles didn't sit well with him. He thought that that was just too random, too messy. But he didn't just reject what he saw because of his preconceptions, and he came to accept it. And like, many scientists that can, feel like they can absolutely, still have some sort of belief and, and be scientists, they don't contradict each other. He said, okay, well, this is the way that, some higher power made the universe. It is still beautiful. It's just not the way I expected it to be. Right.
But
And that's what he found them to be ovals. Go ahead.
Trevor, I remember it like a pretty pink bracelet.
Yeah, that's what it looks like. Yeah, it does. It totally looks like a bracelet. Well, if that helps you remember it, then more power to you. So now, as I mentioned, we're going to officially introduce those 3 laws. And the first one is directly related to that observation that we led up to, the fact that the orbits are not circles. We called them ovals. I said that another word is ellipse. So the planets order in ellipses, and their star, in the case of our solar system, the sun, is at one focus. We'll define what a focus is. This idea of orbits being ellipses is true for moons, which orbit planets, true for comets that orbit the sun, also true for asteroids that orbit the sun or each other. In other words, any orbit is an ellipse. Some of them can be, close to a perfect circle. That's fine. But a perfect circle in a mathematical sense, as you will see in just a moment, is just a subcategory of an ellipse. And because you have to have things work out just right to be a perfect circle, and even then, there's going to be some imperfection depending on how precise you measure it. I mean, think about trying to manufacture a perfect circle, right? Well, what's your level of precision, right? So, same issue here. And when we talk about, the orbits, they will, have this value called eccentricity. But let me get to it. Okay, so before we introduce some of the other, go to circle back to this key term of focus, and more about how to define an ellipse. Let's just notice our picture here. And by the way, there is a mistake in the figure. There's not a big deal, but for some reason they put the arrows pointing the wrong direction, which is kind of an embarrassing mistake. I feel like that they would know they do know better, and someone just must have not caught it. So because all of our orbits in the solar system are counterclockwise. None of them are clockwise. Okay, there's no orbit in the solar system around the sun that is clockwise. And of course, that's from viewed from above, but that's our agreed upon point of view. But anyway, we've got two key points here in our elliptical orbit. The blue dot is the sun, by the way. I'm not sure why it's blue, but the perihelion is the term given to the location in the orbit where the planet is closest to the sun, okay, or comet or whatever. The aphelion is the point where the planet is furthest from the sun. Both these terms have the word helion in them, or which is the kind of derived from helios, Greek word for the sun. So that's where these two terms come from. And the pair is the one that's closest, and the ap is furthest away. Okay, so these are specific terms that refer to these 2 points in a planet's orbit. All right. So I said that the star, or in our case, the sun, is located at one of the focus, is located at one focus. Well, how many of these foci, which is the plural of focus, how many foci are there for an ellipse? There's two. Every ellipse is set up by two foci. Focus one, focus two. Now, on a circle, those two foci merge together into a single point. So when you sort of transition from a ellipse that is not a circle to a perfect circle, you can imagine those two foci coming together and meeting in the middle. And then for a circle, we just have the center. But for all other ellipses, all these elongated cases, there's always two of them. Okay? And the greater distance between the foci is is the more elliptical our ellipse. In other words, it's not a perfect circle. So as you become more elliptical, you get further away from being a perfect circle. And just a heads up, there's two terms here that are kind of easy to mix up and also almost get used interchangeably. And that's eccentricity and how elliptical you are. So this, if we say it's an orbit, this orbit is very elliptical. That's how I would describe it. And I could also say it's very eccentric or has a high eccentricity. Both of those would mean the same thing, right? And we'll get right back to eccentricity, but I wanted to talk a little bit more about one key concept about the ellipse and also a tie-in about how you could make one if you wanted to draw an ellipse by hand as a demonstration of this principle. And the distance from one focus to any point on the ellipse and then back to the second focus is the same. So if I went all the way around the perimeter of the ellipse, that this total distance represented by these two red lines does not change. It's a fixed value, right? So it's always the same total distance. And the way that this can be shown in a demonstration is putting two tacks into like a piece of cardboard, and then having a string that's held taut by a pencil, and then tracing out an ellipse by keeping the string taut, drawing half of it, the top half, and then the bottom half, and that will give you the shape of the ellipse, and that shape will differ depending on how far apart those two tacks are, right? Because that's the principle shown with the string representing that constant distance. Because if you held it tight, it can't vary, right? So here's an example of another point along the perimeter where we have very different distances from the first and second focus, but the sum would be the same. So kind of visualize that and imagine how these two green lines would have the same total length as the two red lines. And even when you're all the way over on one side, if you think of this one blue line all the way across, and then the much shorter blue line that just goes straight over, they would also have the same total length. Okay? All of those would be the same. And if it looks like that the blue can't possibly be the same, that may be because they didn't like make the figure exactly right. But if you did this, like in a mathematical based program or something, or however, you can absolutely show that's the case. Okay. So far so good. Let's check if there's any questions. Right. So continuing with the key parameters. So just kind of established that principle, but just knowing that, although it could let you draw an ellipse by hand, doesn't give you a helpful formula. So basically, in other words, like this idea is great as a kind of a demonstration. I remember doing it in elementary school. It's something that I do sometimes in an in-person astronomy class, and it's sort of a memorable way to think about what an ellipse is.
I
But
had a
we
question.
want to have some mathematical terms. Go ahead.
I had a question about the foci. Like, how would you how would you describe that?
So think of the foci as just two fixed points where the distance from them to the perimeter of the ellipse is a constant. That's really what they are at this point. So
Okay.
so like because you could use them and a because also how I said that the string has to be a fixed length. Well, you choose that length, right? So when you choose the length of the string, that's another like value that you're putting into the system. But if you choose a distance between the two foci, represented by tacks in the demonstration, and you choose the length of the string, then you have set the ellipse. After you've made those two choices, you will draw one unique ellipse, and you couldn't draw anything else. So you can think of that as it would be like a way to fully define the shape in the way a circle is like fully defined by its radius, right? Or a square is fully defined by the length of its side. A rectangle is fully defined by the length of two of its sides, and so on. Like how much do you need to know in order to, completely know this shape? But so I hope that helps with the concept. We actually will circle back around to some other ways to think about the foci.
Okay, cool.
Okay, but as I said, that definition is not helpful mathematically. It doesn't give us an equation. Although there's not too many equations we're going to work with ellipses, but whatever.
Sorry, can you go back to the last slide just for a second? Sorry.
This one,
Yes, thank you.
do you have a question or do you just need to write something down?
Yeah, I was just writing I just need to write the bottom part down.
Yeah.
Is that gonna be on a quiz or a test, do you think?
Yes, that's totally fair game. That's the kind of thing that could come up. Okay. So with it, just to say like kind of a statement I just said again, with a circle, you just got the radius. So circle, all you need to know is the radius. If you know the radius of a circle, you know its circumference, you know its area. So it's literally the only value you need to know. With the ellipse, because they're not symmetric, right? There's not just, one radius. You have to know two separate quantities, and we call those the semi-major axis and the semi-minor axis. And they're just like the radius of a circle, except there's two of them. Okay? Their names are kind of weird. The reason that they're semi is because they're half. They're halfway across. So the semi-major axis is half of the full distance along the longest side of the ellipse. The semi-minor axis is half of the distance across the shortest side of the ellipse. So you have the shortest path across the ellipse and the longest path. The shortest path is the minor axis. The longest path is the major axis. Furthermore, the major axis goes through the foci. It passes through them. The minor axis doesn't. The minor axis is perpendicular to the foci, right? Or perpendicular to the line that connects them. And then just like with circles, we don't usually work with diameter. We usually work with radius. Same thing here. We work with the semi-major axis and the semi-minor axis. Right? So these are the two things that two out of the three things that you need to know to fully describe or define your ellipse. And
So
yeah, go ahead.
is the foci two like I'm not like are they two planets that are orbiting in relation to each other and that's
Oh,
the
hold that,
coordinate?
hold that thought. We'll get back to it.
Okay.
So it's keep just keep wondering. Well, it'll come up. Okay, so the last thing you need, so I said two out of three, are to know the two semi axes, is the focus distance. So this represents how spread out the two foci are. And the focus distance is defined as the distance of either one of the foci from the very center of the ellipse. And the very center of the ellipse is where the two axes intersect, where they cross each other. And that focus distance can be used along with the semi-major axis to come up with our one important formula for eccentricity. And there might be another one I'll put in the homework where we can find the perihelion and aphelion. It's not very difficult. But this is the definitely one you want to know. All right. And it's just a simple fraction, a simple ratio that tells you that the quantity eccentricity, which I mentioned before, but now we're officially seeing, represented by the letter E, no units because it is just a ratio of distances, is the focus distance, which we can see in the figure, divided by the semi-major axis. So that quantity tells you how elongated your ellipse is. So the larger the eccentricity, the more stretched out the ellipse. When the eccentricity is really small and approaches zero, the more circular your ellipse becomes. You can see right here. If the eccentricity is zero, then you have a circle. Again, a circle is a subclass of an ellipse. We don't normally care about that. We just call it a circle. But technically speaking, it is. Okay. And why would an eccentricity of zero be a circle? Well, think about how the equation is defined, which is how eccentricity is defined, right? Is that it's focus distance divided by semi-major axis. Well, for the focus distance for a circle, it would be zero because the two foci will be right on top of each other. Okay? So that's why circles have zero eccentricity by definition. All right. If the eccentricity is one, well, the only way for that to happen is for the focus distance to be equal to the semi-major axis. Well, that means that the foci would be all the way on the edge. It's actually not possible. It's not possible to do that. There's no way to have an ellipse that is so stretched out because it's not an ellipse anymore. So mathematically speaking, we would say that the eccentricity approaches one. And if it was to actually equal one, it wouldn't be an ellipse anymore. It would just be a straight line. It would just be, if it was a planet in motion, it would just be straight forward motion. All right. But that doesn't really concern us more than as an abstract idea that we can get closer and closer to an eccentricity of one, which would be a really stretched out. So imagine you got an eccentricity of 0.99. That'd be a really stretched out, ellipse because the foci would be really close to the edges, right? Here, they're not in the middle, right? But they're not like right next to the perimeter. Well, if you had a really high eccentricity, then they would be. And I gotta repeat one thing as well, that what's easily missed is that range of eccentricity. So please take note that eccentricity can vary between 0 and 1, and that's it. You cannot have an eccentricity greater than 1. By definition, it's impossible. It can't be exactly equal to 1 either, because then it's not an ellipse. And the smallest that the eccentricity can be is 0, which is a perfect circle. It can't be negative. Okay, so it can only vary between 0 and approaching 1. So all of our ellipses and their various, eccentricities, which just describes how stretched out they are ovals. They're all in that range. Okay, so a couple examples of eccentricity. We've got an eccentricity of 0. Notice there's just a single dot at the center because it's a perfect circle. The two foci have overlapped each other and just become, the center. Usually, we don't call it the focus when it's a circle. It's just the center. All right, but look, now we have one with an eccentricity of 0.5. Okay, still fairly circular, right? But not a perfect circle anymore. This is now a ellipse with what you could say with a moderate eccentricity. 0.75, so higher eccentricity, 0.95. Okay, these are all cases of different eccentricities. They've all got those two foci, which is going to get us back to what do they represent, right? There's 0.99. Okay, and here's a quick note about the actual eccentricities. So before we get back to what the foci represent, just take note, these are the actual values that have been carefully measured for the 8 planets and for Pluto. They're pretty small for the most part. So a lot of orbits are pretty close to perfect circles. Mercury does have a noticeable eccentricity in its orbit. It's the only planet that does. Okay. Dwarf planets and comets tend to have higher eccentricities. Pluto is no exception. But of the major planets, notice Mercury is the only one with an eccentricity greater than 0.1, right? And some of the planets have very small eccentricities. Venus has an orbit that is, almost a perfect circle. Its variation from a perfect circle is, we see it just, it think about that as just being a thousandth, and already what does eccentricity represent? You know, even when we saw an eccentricity of 0.5, it still looked fairly circular, if you remember. So if you just looked at Venus's orbit, shown accurately on like, a representation, a figure, it would look like a perfect circle. You could not tell, if even it was printed on the size of a full page, that it wasn't a perfect circle. All right. I actually don't know what they're trying to ask here. I looked over it so many times and just couldn't figure it out. This is showing if you made like a model of these orbits, how the difference between the semi-major and semi-minor axis, which kind of represents how elongated the ellipse is, would be pretty small for all of the planetary orbits, and it doesn't in feet and inches and so on, to kind of think about it as a very large model. Okay, so we had a question a few minutes ago about and then we'll take a break right after this. I know we're due for one, but we had a question about what the heck are the foci, right? Which was great. Is like I planted someone in the audience to ask that question because I wanted you thinking about that, and here we have it. Okay, so you're not expected to know necessarily. I just want your best guess. So planets orbit in ellipses, and their star is at one focus. Okay, so the planet, like the little black dot here, it's going to follow an orbit, not in this direction, by the way. Right, it's going to be counterclockwise. And what the heck in that case is at the other focus? If the sun is at one focus, what's at the other one? So, what do
Nothing
you think?
special.
Nothing special? All right. So it's just like blank. Yeah, it is. It's like, and think about it this way. It doesn't matter which focus the sun is at. It's just at one of them, and the other one is empty. And that's the way orbits work. The gravitational tug comes from one focus, but it's totally interchangeable which one it is. And the other focus has nothing at it. It's just empty space. All right. All right. Do we have a question? Elizabeth?
Yeah, so the planets that have a moon, how would that look like? Would that be on the same orbit or would that be an entirely different one around that planet?
Yeah, it would be around the little black dot. And then the orbit, like the orbit of moons is much, much smaller than the orbit of the planet around the sun. So like if you were to try to show it, it'd be too small to even see. That make sense?
Yes, it does. Thank you.
Yeah. And what last thing I'll say on that, so someone actually asked a really similar question in the other section, is that if we just think about the numbers, and hopefully this helps, you've got okay, so it's 150 million kilometers on average from Earth to the sun. So let's just call that 150. Okay, so let's make our unit million kilometers. Well, the distance from Earth to the moon is 300,000 kilometers. Well, that's about a third of a million. So you got 150 as your distance from Earth to the sun, but then a distance of a third, so zero point 0.3 from Earth to the moon. So it's about 450 times further to the sun than it is to the moon. And so if you drew that on this figure, what would be 450 times shorter than the distance between the blue dot and the black dot? Well, it'd be tiny, right? It'd just be like 1 pixel or something. Yeah. All right. So we are at a natural stopping point. Um, before we well, yeah, because this is a good question, but takes a little bit longer. So we'll go ahead and take our break. We'll come back at 9:18, and then we'll get to the rest of our laws about planetary motion. Good. Share this. Right. Sorry for giving away the answer on that one. Okay. So maybe you just glanced at it. You didn't take note of what the answer was because this one is pretty thought-provoking. And it's totally I would expect most of you to not quite be able to reason it out, but try. Okay. And it's also you have to read it carefully because it's got the whole planet A and planet B. So I'll try to help with that and clarifications. So we got two planets, A and B. They both have the same semi-major axis. So in other words, like this this blue dot or blue line, excuse me, this blue line for both of them is the same length. It doesn't change. What does change is the eccentricity. So imagine like if you kept the same distance from the center, okay, the center of the ellipse, halfway between the two foci, and to the edge, but you varied the distance between the two foci, which itself will vary, how stretched out your orbit is. Okay, so you're keeping the blue line constant, but you're varying the eccentricity. right? Which by the way, would create like a different circumference, right? Because it's like we're keeping that, the one value fixed. Okay, but which one is more eccentric than the other? So planet A has a much larger eccentricity, so there's extra than there, than planet B. I meant to fix that because I saw that last time. But anyway, still readable. Planet A has a much larger eccentricity than planet B. So they're not both showing. Maybe you could think of this one as planet A since it looks pretty darn eccentric, right? And imagine another orbit for planet B that's nearly circular, where those two black dots are almost on top of each other. So, with that in mind, here's your question. Which planet has a shorter perihelion distance? What would it be? Who can tell me? Oh, I see something in chat. A, okay? The Maxwell says it's the more eccentric one that has the shorter perihelion. Does everyone agree?
Yes, planet A.
All right. Okay. That is absolutely right. And maybe it makes sense to you all, and that's great. But I'm going to explain it a little bit more because the next couple slides show it really clearly. Okay, so here we have our two equal semi-major axes, the shared semi-major axis for planet A and planet B. Now let's draw some orbit around that major axis. The foci are not shown, right? But we know that one of them is very eccentric, A, but B isn't. Okay, so now we've made them match the descriptions. Eccentric, highly elliptical orbit for A, nearly circular orbit for B. Right? And then what do they share? They share the semi-major axis. As we can see, that blue line's the same length. It's the shape that is different. Okay, larger eccentricity for A, smaller eccentricity for B. Okay, well, now if we put in the foci where let's have the black dot actually represent, we'll have the green dot actually represent the sun, all right? And the black dot is just the empty focus. So we've got our two foci in both cases. The colored one actually has the star or the body that's being orbited, and the black is empty. Okay, so then if we take the two different orbits and we put them on top of each other so that we line up the focus, so we're lining up the focus for both of them. And you can see that, right? Because look where the blue dot is relative to the nearly circular purple. Okay, there it is, right? But then the green dot relative to the highly elliptical, sort of golden colored orbit, well, it's much near the edge. So when we line them up, we have to line them up like this. And when we do, we can really clearly see which one has a shorter perihelion, and it's the more elliptical orbit because the distance from the sun to that point of closest approach is much smaller for the really elliptical orbit. Okay? So this question really just encapsulates a lot of the ideas and really kind of puts it to the test. So I think it's a good concept question. Hope you agree. Okay. So now finally on to Kepler's second law. The reason it took so long to talk about Kepler's first law is because we had to clear up so many definitions of what an ellipse is. Now that we got that out of the way, Kepler's second law is much faster to talk about, even though it actually kind of has more utility. And as a sentence, the law states that the line between a star and a planet sweeps out equals in equal time. Okay? So it's an equal sweep in equal time. So the line between the star and the planet sweeps out equals in equal time. So in other words, the area that is swept out, and I'll show what that is in the slide here, is going to always be the same in the same amount of time. Okay? And just like all of Kepler's laws, it holds for all orbits. All right, so let's consider some date in the orbit of, for example, the Earth around the sun, although this ellipse is more elliptical than Earth's orbit, but just for the sake of showing it clearly. So we consider some point in the orbit December 1st. Okay. Well, later in the orbit, we have January 3rd. And do note, because I mentioned this sort of weird mistake with the slides, the arrows show an orbit going in the clockwise direction. But here, obviously, the dates and the orbit of Earth is going in the counterclockwise direction, right? December 1st, then January 3rd. So the dates are correct in their direction. The arrows are not. And I don't know why they wouldn't have changed that, and how why they would have published these slides in such a big typo. All
So
right,
all orbits are clockwise or counterclockwise?
counterclockwise.
Okay.
All orbits around the sun are counterclockwise. So then let's consider a point that's about 2 months. Okay, so this is a 2-month time period from December 1st to January 31st. Because months obviously vary in the number of days, so we'll just think of this as like 60 days, right? Which I think is the right number. Okay, depending on if you include the endpoints or not. But importantly, we're going to do the same thing on like 6 months later. So when the planet is on the opposite side of the sun, or another way of saying that, when the planet is at aphelion, because these dates, December to January, like the end of January, they correspond to when the planet is at perihelion, closest to the sun. And then we're going to look at dates in, late spring, early summer, where the planet is furthest from the sun, when it's at aphelion. And incidentally, that actually is how our planet orbits the sun. It's closest to the sun in the northern hemisphere winter and furthest from the sun in the northern hemisphere summer, which just goes to show that our distance from the sun does not affect our seasons. It does not significantly affect our seasons. It's just our axial tilt. But we'll come back to that in chapter 4. All right. So again, 2-month time period during the aphelion, greatest distance from the sun. So we look at these two equal time periods, because that's part of Kepler's second law, that we're interested in equal time periods. And we want to now look at what this idea of sweeping out an area. Well, the sweep are the green region, the shaded green region, and the shaded yellow region. And the idea is that those two regions, the two differently colored and differently shaped regions, green being short and wide, yellow being long and narrow, they are equal in area. So if we took them and we carefully measured them, we'd find that they have the same area despite their different proportions. And why do we know that? Because they're the same time, right? So that is Kepler's second law. In other words, planets go fastest when they're close to the sun, and they slow down when they're further away. Do you see it? Because they have to cover a greater arc. When you got the squat wide area. Okay, so same area. So just to make sure you're listening, when is Earth moving faster through space?
When it's closer to the sun.
Okay, and what months would those be?
December 1st to, I mean, August 1st to June 1st, or June 1st, you know what I mean.
No. You were right the first time. December to January.
Oh, December to January.
Yeah, December to January. That is when it is moving fastest. Yep, 1. Very good. Yep, good work, Maxwell. You got it right. All right. So there we go. And there's your answer. Okay. And that actually is true. We're going faster. All right. All right. Now Kepler's third law. Kepler's third law is the one that is used the most by far, and it relates the period of an orbit to the semi-major axis of an orbit. So what it allows us to do is to compare between planets. It allows us to say that all of the planets are going to have this same relationship, which I'll explain in just a second, shown here between the period represented by uppercase P and the semi-major axis A, which is the letter we've been using for the semi-major axis throughout the slides. We always use lowercase a, right? Uppercase P for period. Period would be measured in years. Could also measured in seconds, but it's more convenient to measure it in years, Earth years. Okay. A, you measure it in meters since it's a distance, but we're going to measure it in astronomical units. Okay. So here, notice the units. There are times when you wouldn't use these units. In a homework problem, I would specifically, warn you when to use them and when not to use them, and that will become more evident with practice. But in this case, we are absolutely going to measure the period in years and the axis, semi-major axis, in AU. Remember that stands for astronomical unit. And then to finally state Kepler's third law, it says that the square of the orbital period is proportional to the cube of the semi-major axis. And it's a proportionality because it's not an equation. And that's what this symbol means right here. This, instead of an equal sign, it's a proportionality sign. It uses a lot in science in general, and the physical sciences in particular. They show up a lot in astronomy. When we don't need or want an equation, we just want a relationship. We just want to know at what rate do these two values change relative to each other. What's great is that with these two units, we can actually basically make it an equation if we just stick to working with the period in years and the axis in AU, and we only compare between planets. And what I'm trying to say there is that as long as you don't compare, the orbits of, say, the moons of Jupiter around Jupiter to the planets' orbits around the sun, then you can just work with the proportionality, and you don't have to make an equation. It's only when you change between what body is being orbited that you have to actually worry about the units. But as long as we're only concerned with the sun as the body that's being orbited, we're good. And to highlight that, let's consider a value here. I think I have it pulled up. Yep. So I'm gonna write down some numbers for periods, or rather for semi-major axis values. Okay, so here's going to be A for the Earth. So A with a subscript of E for Earth is just going to be 1 because, after all, it's measured in AU. Okay, and the astronomical unit is based off of Earth, so it's exactly 1. So if you knew that, because you'd measure that value, and then through careful observation, you're able to find out how far Jupiter is from the sun. And you found out that Jupiter has a semi-major axis of 5.2. So we'll write that down. So here we're going to have the semi-major axis of Jupiter, 5.2 AU. Well, what would be the period of Jupiter's orbit in Earth years? Because we know the period of Earth's orbit, it's just 1 year, so 1y. But what would be the period of Jupiter's orbit? Go ahead. Think about how, so use this proportionality as an equation and find P based off the information I've given you. Find the orbital period of Jupiter.
Orbital period of Jupiter.
Yes. You're solving for PJ.
I'm
I don't know
confused.
how I would begin to solve that. Like, I don't know how I would set it up.
Okay. So think about like how it's defined with the values of year and astronomical unit for Earth. Because if we plug in for Earth, if we just plug in 1 year and we square it, and we, as I said, use the proportionality as an equation, which we can only do because of our choice of units. And then I put in the Earth's semi-major axis, which is also 1. And I cube it. Well, is that a true equation? Is 1 cubed or 1 squared equal to 1 cubed?
I thought it would just cancel each other out because the one.
They don't cancel, but what is 1 squared?
I don't know.
Okay. If you don't know it, plug it into a calculator. And I'll come back to you. What is 1 squared?
Okay.
1, right?
It's just 1, exactly. And what is 1 cubed?
1.
Yeah. So because of our choice of units, we can confirm that it is a valid equation to write p squared equals a cubed as long as we're using Earth years and astronomical units. Therefore, we can find either one of period or astronomical or semi-major axis. So we can find either period or semi-major axis of any other planet if we know one of them. So if we know the semi-major axis, we can find the period, as in the example here. If we knew the period, we could find the semi-major axis. So by choosing year and astronomical unit and sticking with those units, we're able to convert our proportionality into an equation and now use it to find the orbital period of Jupiter. Okay, so that's why and how we can do it. But you're probably interested in what does it look like to do it? Let me just erase if I can. Yeah, so I'm gonna erase down here. And I'm just going to plug in for, it's not 140, but that's a good attempt. That's too big for the orbital period of Jupiter in Earth years. So try again, but you're on the right track. And get back to PowerPoint. Okay. Okay, so now I'm just going to set up the equation again, but instead of putting in the values for Earth, which are 1 and 1, I'm going to leave the period of Jupiter just as a variable, put parentheses around it to remind me that I'm solving for it, square it, and then set it equal to the given value of 5.2 on the right-hand side. All right. And I'm just going to leave off the units just for, brevity, and then cube it. So now all I need to do is solve this equation. I've got a value on the right that's cubed. I've got a value on the left that's squared. And I basically just need to get the pj by itself. How would I do that? what would I do to both sides of the equation to get rid of the square on the PJ term?
Are we dividing?
Kind of, but you don't divide to get rid of a power. You take roots. Does that sound familiar?
Yes, I'm just trying to refresh in my
Sure,
memory.
yeah. And I said kind of because, powers are sort of just like chains of multiplication, but
Right.
practically speaking, you would take the square root of both sides. So what that would look like in terms of just like showing your work is you take the square root of both sides like that, because the square root will exactly cancel. It's a different color here. So the root cancels the square. So the power of 2 gets canceled by the root. And now, just like we wanted, the PJ's by itself. And this is our answer. And we just need to plug that into a calculator.
So I got like 11.85 and some additional numbers.
Heck yeah, that's right. And
Mm.
you'd want to round it. I would tell you how many significant figures,
Okay.
in on like a homework problem. Yep. So
So around
11. Yep.
second,
I don't know.
11 or something like that. Sorry, 86, 11.86.
Yeah,
Perfect.
I got
Yeah,
11.86 years.
that's right. So I can see so did Maxwell did. Yep. Oh yeah, and we got yep. Oh, then Teresa sent it to me directly. Nice. All right. 11.86 is the correct answer. And someone asked me yesterday, would this be on a quiz? No, it's too math heavy to be on a quiz. The concept could be on a quiz, like maybe like a figure where you have to kind of identify the rate of change, the fact that the period is increases with at a as a parabola, right, as a square, and then the semi-major axis increases as a cube, which is a steeper curve. So that those type of ideas would be fair game for our quiz. Another thing that could show up for a quiz is a case where the numbers don't become a decimal, because there's some values where that don't match any real planets, but where the values are like exact. In other words, like it's what is it? Four cubed, no, two, I think 2 cubed is equal to 4 squared. Is that right? Because 2 cubed, 2 times 2, 4 squared. Yeah. Yep. So four squared actually equals 2 cubed. But what's almost most important, besides, all kind of the math aspects of it, which help with getting it done, and I think are, almost necessary for understanding it fully, but then realistically you might not understand everything fully, and sometimes you have to move on. Put the answer in here or past. Oh, sorry, years. Is that?
I thought it was 11.86.
Oh yeah, you're right. 11. With the wrong number.
So is the 11.86 the proportion to Jupiter from the sun?
It's the length of its orbital period.
Oh, in years.
Exactly. And so I wanted to write that down so that was clear. Okay, so there it is. 11.86 years.
I have a question, Mr. Trevor.
Yep.
Can the distance of the 5.2 AUs, can it also be measured in kilometers?
Yes. But then we would need to have we'd have to do more math in that case.
Yeah.
Okay.
I don't want to. I'm just asking because I was
Yeah.
like, I'm using
Yes.
a
And
calculator from statistics and it's telling me like it shows me something different too, like that you can measure that in kilometers, the AU.
oh, right. Yes, you can. You can convert AU to kilometers. The conversion is 1 AU is 150 approximately million kilometers.
Okay.
Okay. And there's a version of Kepler's third law, which we may get to in the next 20 minutes, that that where we would use kilometers. Okay. And so it's just a few slides down, and we just need to introduce something about Newton's law of gravity first.
Okay.
But yeah, for now, this version of Kepler's third law, you want to use years and AU. The last thing I want to say, because this is kind of like I think it's the most important takeaway, like, how do you make sense of this, see a trend? Okay, it's this. Notice that the semi-major axis of Jupiter is 5 times, 5.2 times bigger than Earth's. In other words, Jupiter is about 5 times further from the sun than Earth. Cool. But its year is almost 12 times longer. That's what Kepler's third law tells us, is that as the distance goes up, the length of the orbital period goes up even more. You see it? So it's like for every greater distance from the sun, the length of that planet's year gets even longer, comparatively longer. And it's because of this relationship between squared and cubed. Because if you're cubing something, if you're cubing the semi-major axis, it's growing really quickly. But if you're only squaring it, it's not growing as quickly, which means that P itself has to be bigger in order to catch up with A, because A has the advantage of being cubed. So that means that the period has to be longer for a particular value of A. Yep, 2 cubed equals 8. Oh, 2 cubed equals 8, so it doesn't work. So then it's 4, maybe it's 4 and 8 then. Because 8, all right, I do in my head. So 8 squared is 64, and 4 cubed is also 64. So that's kind of the famous one, is that if your period um is 8, then that could be, so a period of 8 years, for example, would be equal to a semi-major axis of 4 AU. Because 8 squared, I was here, I put it in chat. 8 squared equals 64. So that would be on the period side. And then 4 cubed also equals 64. And so then we can say thus, a planet with a period of 8 years has an orbit of 4 AU. So that's one of the only times where you don't end up with decimals, because you have a square that's equal to a cube.
So I had a question.
Go ahead.
Um, so where it says period two proportion, I don't know how you say it, but like in proportion to
Mhm.
axis 3, that is the equation for the semi-major axis, and then once you solve it, that's how you figure out um the the uh the length of the orbital period.
Yeah. In the example that we just did, that I came up with, we solved for the length of the period. We
Okay.
could have solved for the semi-major axis instead. I could have given you P and asked you to solve for A. It would have been very similar.
Okay.
Yeah.
And then those where it says P2 and A3, is that's squared? I mean that.
Yeah. Yep. Yeah. The P is squared, the period P is squared, and the semi-major axis A is cubed, which just means raised to the power of 3.
So P is squared, A is cubed.
That's right.
And what's the difference between squared and cubed?
It's how many times you multiply by itself. So P squared is P times P, a cubed is a times a times a.
So for the P, it's always going to be squared and the A is always going to be cubed.
Yep, that's exactly right. That's what Kepler found. That's the key thing, the key discovery, is that this relationship always holds. And it really was kind of his greatest finding because no one could have guessed this. It's not something that you would just come up with, but the data showed it. All right. Okay, I'm going to move on. We can get through a little bit more. Obviously not trying to rush, but we want to cover a little bit more. All right, now we're done with Kepler for now. What we're going to talk about for the next few minutes, next 10, 12 minutes, is going to be Newton. Okay. First, let's go back to our timeline real fast. I won't get into this too much in the interest of time, but we're going to add a little bit past 1642 because we've been dealing with this range of time from 1473 up to 1642, which is the death of Galileo. And we haven't gone further into the future. All we did so far is just add in Tycho Brahe and Johannes Kepler. But now we are going to go past into, the rest of the 17th century, so the later half of the 1600s, and into the early 18th century, so up to the early 1700s. And that time span, 1642 to 1726, is the life of Isaac Newton, perhaps tied for the best known scientist along with Albert Einstein. And he made a publication where he introduced his theories on motion, gravitation, and also invented calculus. Calculus, mathematics that is just a real workhorse of doing everything from engineering to astronomy and everything in between, did not exist until Newton came up with it. And it was invented by him, just derived, worked out, proved as a mathematical method because he needed new mathematical tools to answer the questions that he was interested in. Questions about orbits, about gravity, and also about light, which we're not actually interested in his research on light, but he did study it as well. And here's a quote from him, which where he's pointing out that from his point of view, he's not totally unique. He just was kind of in the right place at the right time, able to bring ideas together. Okay, let's run through Newton's laws of motion. I'm just going to briefly cover these. He came up with 3 laws of motion, and these are separate from Kepler's laws of orbit. We actually can show with modern physics and astronomy and astrophysics that Kepler's laws are not different than Newton's laws. So Kepler's laws of motion can be derived from Newton's laws of motion. So Newton's laws of motion are the fundamental ones. That said, they look a bit different. They can definitely serve different purposes, and it's practical to have both sets. Okay? Because to actually derive Kepler's from Newton's is not an easy task. Okay, so what are they? So Newton's laws of motion, the first one is called the law of inertia. This one's pretty well known in terms of people like to state it. And it says that an object at rest or in a state of uniform motion will continue that motion unless acted upon by an outside force. So you can't move or change your direction without a force. Things in the universe don't just spontaneously move. They need a force. Examples of that, if you ride in a car, you slam on the brakes, you have inertia, and if you don't have a seatbelt to exert a restraining force on you, you'll just continue to move, right? because that's the idea. That's your inertia, which is based off of your mass and the fact that it resists change. And the only way to change it is with a force. And by it, I mean anything that has mass. Okay, the second law of motion is called like the law of acceleration and is a well-known formula, and it's F equals ma. I imagine some of you have seen this formula before. It shows up in popular culture from time to time. And so it's just F equals ma. What does that tell us? Well, it tells us that the force is equal to the product of mass and acceleration. And as a statement, the acceleration of a body is proportional and in the same direction as the net force acting upon it, and inversely proportional to the mass of the object. That's a long sentence. What it's telling us is that acceleration and force point in the same direction. If you got a greater force, you got a greater acceleration. If you have you push on the gas pedal and cause a greater force between the tires and the pavement, you're going to speed up faster in your car. If you're in a rocket and you've got a greater thrust coming out of your engine, then that rocket's going to speed up faster. And speeding up is acceleration, because acceleration is how fast your velocity is changing. Acceleration is the rate of change of velocity. So if you have a big acceleration, you're changing velocity fast, okay? Because of bigger force. But what does the whole inversely proportional thing mean? What's inversely proportional? That just means that you have a relationship where if one thing grows, the other thing shrinks. So anytime a relationship between two values causes one to go down as the other goes up, we call that an inverse proportionality. And in this case, there's an inverse proportionality between force and mass. Okay. Or we got maybe more accurately between acceleration and mass for a constant force. So if I push on something with the same amount of force, and then I push on something else that's much heavier that has a greater mass, but I don't change my force, well, the less massive object is going to be accelerated more easily than the more massive object. So that's what the law tells us, is that it's harder to accelerate bigger things that have more mass. And the last law of Newton's three laws of motion is the action-reaction law. This one states that for every action, there is an equal and opposite reaction. When we say opposite, it means opposite direction. So if I push on the floor pushes back on me, which actually I'm so used to saying that, but I know it kind of sounds strange when you first hear it. It's called the support force or the normal force. But there's lots of examples of that. There's no case where any system, any object can exert a force on something and not have the exact equal force exerted back onto it. And this is actually really is so crucial to understanding how forces work, this third law, and clears up all of the confusion that can exist without this law. There's tons and tons of examples. Here they mentioned launching a rocket, because what a rocket does is it pushes that exhaust out of it, the back, right? So you have this like pressurized gas coming out of the back of the rocket. Well, why does that cause the rocket to go forward? Well, because the gas pushes back on the rocket. So, if you accelerate gas out of the back, well, then the rocket has to accelerate the opposite way. Other examples of this would be like if you imagine like if you're on like a lake and you've got two boats, if you push one boat away from you, you also drift away. You can't push a boat if you're just floating out on the water and not also float, also move yourself. But you can see that there's always that reaction force. Or if you imagine two people on ice where the ground is really slippery, if one person pushes another away, they also slide backwards. Okay, and that's all because of this action reaction law. Okay, So just to kind of get to a good stopping point with this whirlwind introduction of Newton's laws, the one that we actually care about the most are not Newton's three laws of motion, but what is sometimes called Newton's fourth law, which is the universal law of gravity. So this is the law that Newton came up with that explains gravity. All right? Because Kepler's laws don't. Kepler's laws are great. They're accurate and they let us predict the motion of planets, but they don't explain gravity. They don't tell us how strong it is. They don't tell us if it's how it's dependent on distance and mass. All right? But Newton's universal law of gravity does. Okay, so as a statement, gravity causes attraction between objects with mass. In other words, all mass attracts all other mass. That's why planets orbit stars. That's why the moon orbits Earth, because the moon is attracted to Earth. Earth is also attracted to the moon. These two massive, chunks of rock and metal floating in space are attracted to each other. Why do we orbit the sun? Because the mass of Earth is attracted to the mass of the sun, and vice versa. Okay. And you might think, wait, the sun is also attracted to Earth? Well, it is, but it's just a much smaller force. So it doesn't really affect things. So the force that really matters is just the attractive force from the sun rather than the one from Earth. So here we got two objects. Think of them as just blobs in space. They each have a mass, therefore they each experience an attractive force towards each other. Right? And I think a second ago I said that the force is much bigger. It's not that the force is bigger between the sun and the earth. It's the acceleration that changes because the forces have to be equal. But the effect of the force on earth is much more dramatic. All right. So both objects are attracted to each other. They feel the same size force pulling them together. They have to, because otherwise it would contradict Newton's third law. Right. So you can think of it as that idea that the force of attraction has to be equal and opposite is just built in to the universal law of gravity because it can't contradict one of the other laws, right? If you bring them closer, the attraction gets bigger, okay? And here it is. Here's our stopping point here. This is the universal law of gravity. It is an equation, not a proportionality, that relates the force of gravity between two objects of mass 1 and mass 2 that are a distance r apart. And to make it an equation, you have something called the universal constant of gravity, big G, and this is its value. This is a universal constant, first one we've seen. Okay, it sort of like defines how our universe works, and it was measured experimentally. All right. Are the dates meaning when they were born and died or something else? Oh, yes. Yeah, the dates on the timeline are born and died, not like career. Yep. Yep. Sorry to answer your question sooner. All right, so we're at a good stopping point. We're gonna put a pin in it here. There's not too many like slides left that actually introduce anything. There's just a lot of practice questions. We'll do those absolutely first thing Monday, and then as soon as we have all those practice questions fresh on our mind, we'll do the quiz, which will be kind of more of the same. So it'll be a good segue, I think. But there's not too much that we have to finish on this last bit of lecture 3 covering chapter 3. Let me stop the recording.